Hi, my name is Kelsie Wentz, and I was a 2023 Arnold Beckman Postdoctoral Fellow. This fellowship in chemical sciences allowed me to pursue research at Johns Hopkins University in the lab of Professor Rebecca Clausen. My research project focused on the synthesis of new materials containing silicon as a means to improve current electronic technologies. To introduce my Beckman Foundation funded research, I want to relate it to an everyday application that everyone is familiar with. Consider the technology that you're currently using to watch this video. Electronic devices are crucial parts of our daily communication, work, and leisure time. These devices are powered by electricity, which is the flow of electrons throughout your device. For example, when you're charging your cell phone, free electrons are flowing through the outlet, down the charging cable, and into your cell phone. To make better devices or discover new applications, it is important to have a basic understanding of newly designed materials at one of the smallest levels, the molecular level. The main idea of my research project was to understand how the incorporation of silicon, a solid material that is known to allow electrons to easily flow throughout it, into a material that doesn't allow electrons to flow as easily. Consider slime, for example. It is a very soft and flexible material made of many parts strung together, but it is known to not be a good electronic device. And why is that, you might ask? Well, it comes down to differences at the molecular level, which is what my research has aimed to do. To further understand what happens when you incorporate two known materials into one unknown new material. This basic understanding from my research project is beneficial for understanding how we can improve current technologies. For example, like making new electronic devices as the ones shown, ones that are stretchy, durable, and can be used for flexible display screens or solar cells. To gain a basic understanding of the new materials I have made as a postdoc, an invention by Dr. Arnold O. Beckman has been crucial. In the 1940s, Dr. Beckman designed the first spectrophotometer, which is an instrument that allows us to understand how light interacts with materials. Generally, the addition of light to a sample causes two things to happen. Some of the light is absorbed by the material, and the other light is allowed to pass through. The light that gets absorbed by the material gives it more energy and causes electrons to freely move throughout the material. Using the spectrophotometer to measure exactly what wavelength of light causes the electrons to move helps us understand how these materials behave and what applications they could be suitable for. This same instrument that chemists use in the laboratory is useful for analyzing blood to detect diseases and also measuring amounts of chemicals in swimming pools. Like all modern technology has evolved over the years, the spectrophotometer Dr. Beckman invented in 1941 has evolved into the Carey 60 spectrophotometer on the market today, and the one that I've used in my research. Without Dr. Beckman's design and invention of this instrument, we would not be able to understand the basic structure of new chemicals, leading to transformative discoveries in energy, medicine, and national security. Throughout my postdoctoral work, I developed new strategies to incorporate silicon into softer materials. At the molecular level, I found that the addition or removal of electrons results in the breaking of the bond between silicon and allows electrons to easily flow throughout the material. In summary, my work has provided a basic understanding of how electrons move in softer silicon-containing materials. This understanding could be used to design more energy-efficient electronic devices or solar cells, in the same way that doctors have to understand how a virus like COVID works and is transmitted before they're able to develop effective treatments. My Arnold O. Beckman Postdoctoral Fellowship granted me the opportunity to work on a cutting-edge research project while also giving me the chance to become an independent leader and innovator in synthetic chemistry. This postdoctoral fellowship afforded me chances to extend my network, develop new collaborations, learn new skills and techniques, and ultimately continue my academic career as an assistant professor at Indiana University. For that, I'm extremely grateful to the Arnold and Mabel Beckman Foundation for providing me a means to investigate chemistry that excites me, while also giving me the professional development needed to help me reach my dream career goals.